Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Hello viewers, trust you are all doing fine. I am happy to share with you that your SPEC eLearn channel has reached 1000 subscribers. This achievement was possible because of the motivation you have been providing to us for the past 1 year and the trust you have placed on our ability to provide quality content to enrich your knowledge and develop your skill. Thank you all once again. GATE 2022 Chemical Engineering Previous Year Questions and Solution. In this video, I have combined year 2014 and year 2019 questions to give broader view of the question paper and the types of questions. I hope you will find it useful. Fluid mechanics. In this video course, we will see GATE 2014 question number 12, question number 13, question number 18, question number 39, question number 50. GATE 2019, question number 6, question number 23, question number 28, question number 29, and question number 41. I would appreciate if you subscribe to the channel. It will motivate us to produce more valuable knowledge content for your career progress. So subscribe now before you forget. GATE 2014 question number 12. In case of pressure-driven laminar flow of a Newtonian fluid of viscosity mu through a horizontal circular pipe, the velocity of the fluid through the pipe is proportional to option A, mu, option B, mu to the power 0.5, option C, mu to the power minus 1, option D, mu to the power minus 0.5. For a laminar flow through a horizontal pipe, the pressure drop equation is expressed as delta P equals 32 mu L U divided by D squared. Rearranging the expression for velocity, we get U is equal to delta P D squared divided by 32 mu L. In this expression, you find the velocity is inversely proportional to mu. Hence, the answer is C. GATE 2014 question number 13. Which of the following statement is correct? P. For rheopectic fluid, the apparent viscosity increases with time under constant applied stress. Q. For a pseudoplastic fluid, the apparent viscosity decreases with time under constant applied stress. Or, for a Bingham plastic, the apparent viscosity increases exponentially with applied stress. Yes, for a dilatant fluid, the apparent viscosity increases with increasing deformation rate. The options A, P and Q only, B, Q and R only, C, R and S only, D, P and S only. Before you select the right option, understand the correct statement with respect to how the viscosity changes with applied stress over time. Pseudoplastic is a fluid whose viscosity decreases under shear stress but remains constant over time. Brigham plastic is a material for which the viscosity decreases when the applied stress exceeds a certain minimum value. Going by the above explanation for pseudoplastic and Bingham plastic, the statements Q and R are incorrect. The statements P and S are correct. Hence, the answer is D. GATE 2014, question number 18. Slurries are most conveniently pumped by option A, syringe pump, option B, diaphragm pump, option C, vacuum pump, option D, gear pump. A. Syringe pump is a positive displacement or piston pump typically used for precise dosage of drugs and infusion fluids to patients in small volumes. It is used in laboratories and not intended for industrial use and slurry services. C. Vacuum pumps is used for pulling vacuum and handles gases and vapors, not used for transporting liquids or slurries. D. Gear pump is used for pumping clean liquids. Slurries will cause damage to rotating parts such as gears due to close contact between the moving gears. B. Diaphragm pumps uses flexible diaphragm to pump liquids at high pressures. The forward and backward movement of the diaphragm pumping action is caused by hydraulic fluid pushed by a piston. Shown in this sketch is a diaphragm pump. A diaphragm pump is a positive displacement pump that uses a combination of reciprocating action of a rubber, a thermoplastic, or Teflon, or a metal diaphragm, and suitable valves on either side of the diaphragm, like check valve or ball valve, to pump a fluid. Diaphragm separates the processed liquid slurry from the hydraulic fluid and piston. Diaphragms can be made of several materials from Teflon to stainless steel, depending on the nature of fluid. Hence, the answer for the question is B. GATE 2014, question number 39. An incompressible fluid is flowing through a contraction section of length L and has 1d x direction steady state velocity distribution as follows: U equal to U naught times 1 plus 2x divided by L. If U naught is 2 meter per second and L is 3 meter, the convective acceleration in meter square per second of the fluid at L is. Before we move on, I would like to make a call to my dear viewers. Your SPEC e-learn channel is one-stop learning and skill development destination for your career needs. Get instant access to useful career-oriented subjects and become knowledgeable and competent. So do not forget to subscribe. Please press the subscribe button now. Before we go to the solution part, let me explain the concept first. Convective acceleration is the velocity at a point multiplied by the velocity gradient at that point within the fluid flow. We are given the one-directional velocity distribution in x direction. Hence, the problem is reduced to one-directional. Hence, in x direction, the convective acceleration Ax can be written as Ax equal to u times du by dx. This sketch shows the contraction section of length L through which the incompressible fluid is flowing. The fluid enters the section at a velocity u0 equal to 2 meter per second. The velocity distribution u in the contracting section is given as a function of u0 as shown. You are required to determine Ax at x is equal to L equal to 3 meters. From the velocity distribution, find out the velocity gradient du by dx first. We are given that u is equal to u0 times 1 plus 2x divided by L. Differentiating this expression, we get du by dx equal to u0 times 2 by L is equal to 2 u0 by L. Substituting the values of u0 and L, we get du by dx equal to 4 by 3, 1 by s. The velocity u at the point x is equal to L is equal to 3 meter per second is calculated from the expression for u, which works out to 6 meter per second. The convective acceleration at x is equal to L equal to 3 meter is Ax equal to u times du by dx, which is equal to 6 times 4 by 3, which works out to 8 meter per second squared. GATE 2014 question number 50. In a steady and incompressible fluid of density 1.25 kg per meter cube, the difference between the stagnation pressure and the static pressure at the same location in the fluid flow is 30 mm mercury, which have density of 13,600 kg per meter cube. Considering the gravitational acceleration as 10 meter per second square, the fluid speed in meter per second is There are two terms in the problem. One, stagnation pressure Ps, static pressure P. The pressure at a point in a fluid is called static pressure. The stagnation pressure is the pressure that the fluid would attain if it is brought to rest without loss of mechanical energy. The Bernoulli's equation for fluid flow in pipe at 2 points 1 and 2 with no elevation change is written as P1 by rho g plus U1 squared by 2g equal to P2 by rho g plus U2 squared by 2g. Designate point 1 as static point and point 2 as stagnation point. P is the static pressure at point 1. U1 is the velocity at point 1. P2 equal to Ps, that is stagnation pressure. U2 is equal to 0 because the fluid has come to rest at this point. With U2 is equal to 0, the Bernoulli's equation simplifies to P by rho g plus U1 squared by 2g equal to Ps by rho g. Rearranging this equation, you get U1 squared by 2g equal to Ps by rho g minus P by rho g. So U1 becomes square root of 2 times Ps minus P divided by rho. It is given that the difference between the stagnation and static pressure at the same location is equal to 30 mm mercury. The density of the mercury is 13,600 kg per meter cube and G is equal to 10 meter per second squared. Applying this data, U1 becomes square root of 2 times 13,600 times 10 times 30 times 10 to the power minus 3 divided by 1.25. U1 works out to 80.8 meter per second. So the answer is that the fluid speed is 80.8 meter per second. GATE 2019 question number 6. For a fully developed turbulent hydrodynamic boundary layer for flow past a flat plate, the thickness of the boundary layer grows in thickness from the leading edge of the plate along the free stream flow direction as option A, x to the power 0.5, option B, x to the power 1 by 5, option C, x to the power 0.4, option D, x to the power 0.8. For flow over a flat plate, the boundary layer thickness grows continuously from the start of fluid plate surface contact, that is a leading edge, along the free stream flow direction as shown in this figure. It is a function of a distance from the leading edge x and not a constant as shown in this figure above. For a fully developed turbulent hydrodynamic boundary layer past a flat plate, the thickness of the boundary layer delta increases with distance x from the leading edge of the plate. The thickness of the boundary layer delta x in the fully developed turbulent regime is expressed as delta x equal to 0.16x divided by Reynolds number to the power 1 by 7. The Reynolds number is also called the local Reynolds number Rex is expressed as Rex equal to rho u x divided by mu. Rex is an important flow parameter for internal flows and is also expressed as a function of distance x. Thus, we rewrite the expression for delta x in terms of x for the same fluid. Delta x is proportional to x by x to the power 1 by 7. Simplifying, we get delta x proportional to x to the power 0.8. So the answer for the question is option D. GATE 2019 question number 23. For a hydraulic lift with the dimensions shown in the figure below, assuming G equal to 10 meter per square second, the maximum diameter D left in meter that lifts the vehicle of mass 1000 kg using a force of 100 Newton is. This figure shows the hydraulic lift that is used for lifting the vehicle. You have to determine the maximum diameter D left. The data given are mass of the vehicle 1000 kg, force applied to the lift to the vehicle is 100 Newton, the diameter of the lifting platform of the vehicle is 2 meters. To lift the vehicle, the condition is the pressure applied on the left should be greater than or equal to pressure acting on the platform on the right side of the lift. The force applied on the left is 100 Newton. So the force converted into kg force equal to 100 by 10, which works out to 10 kg force. The area on which the force is applied, A left, is equal to pi d left squared divided by 4. The area on which the weight of the vehicle is acting, A right, equal to pi d squared by 4, which equal to pi 2 squared by 4, which works out to pi meter squared. The pressure is force per unit area, that is P is equal to F divided by A. Converting and equating the two pressures applied on both sides of the lift, we get 10 times 4 divided by pi d left squared equal to 1000 times G by Gc divided by pi. G by Gc is mass to force convection factor, which is equal to 1 for the unit chosen. Solving for d left, we get d left squared is equal to 1 by 25. So d is equal to 0.2. GATE 2019 question number 28. An incompressible Newtonian fluid flows in a pipe diameter d1 at volumetric flow rate q. Fluid with the same properties flows in another pipe diameter d2 equal to d1 by 2 at the same flow rate q. The transition length required for achieving the fully developed flow is L1 for the pipe diameter of d1, while it is L2 for pipe diameter d2. Assuming steady laminar flow, the ratio L1 by L2 is option A 1 by 4, option B 1, option C 2, option D 4. This figure shows the boundary layer in the entrance region of a pipeline in the case of a steady state laminar flow of fluid through a pipe of diameter d. A boundary layer in which viscous effects are important is produced along the pipe wall such that the initial velocity changes with distance along the pipe x until the fluid reaches the end of the entrance length. Beyond the entrance length, the velocity does not change with x, that is, du by dx is equal to 0. Boundary layer grows in thickness in the entrance region to completely fill the pipe in the fully developed region. Viscous effects are of considerable importance within the boundary layer. Outside the boundary layer, the viscous effects are negligible. The shape of the velocity profile in the pipe depends on whether the flow is laminar or turbulent. Similarly, the entrance length depends on whether the flow is laminar or turbulent. The entrance or transition length from a pipe entrance to the point where fully developed flow occurs in a laminar flow is determined from the expression Le by D equal to 0.06 Re. where L is the entrance or transition length, D is the diameter of the pipe, or E is the Reynolds number. In the fully developed flow, the velocity does not change with streamwise direction, that is in the direction of flow. So du by dx is equal to 0. To solve the given problem, first you have to find out the relationship between the velocities of the fluid in the two pipes. The data given for the two pipes are d2 equal to d1 by 2. Flow is the same in both the pipes. Hence, q1 is equal to q2 is equal to q. Also given that the properties of the fluid is the same in the two pipes. So expression of the flow is q equal to u into a. Since the flow is same in both the pipes, u1 into a1 equal to u2 into a2. So that is u1 into pi d1 squared by 4 equal to u2 into pi d2 squared by 4. Substituting d2 equal to d1 by 2 and simplifying, we get u2 equal to 4u1. Now use the expression for the transition length for the two pipes. For the pipe 1, L1 by d1 equal to 0.06 times d1 u1 rho by mu. So L1 equal to 0.06 times d1 u squared into u1 rho by mu. Similarly, for the pipe 2, L2 by d2 equal to 0.06 times d2 u2 rho by mu. So L2 becomes 0.06 times d2 squared into u2 rho by mu. Substituting d2 equal to d1 by 2 and u2 is equal to 4u1 and simplifying, we get L1 by L2 equal to 1. So the answer is option B. GATE 2019, question number 29. Your disk turbine is used to stir a liquid in a baffled tank. To design the agitator, experiments are performed in lab scale model with a turbine diameter 0.05 meter and turbine impeller speed of 600 rpm. The liquid viscosity is 0.001 Pascal second, while the liquid density is 1000 kg per meter cube. Before we move on, I would like to make a call to my dear viewers. Your SPEC e-learn channel is one-stop learning and skill development destination for your career needs. Get instant access to useful career-oriented subjects and become knowledgeable and competent. So do not forget to subscribe. Please press the subscribe button now. The actual application has a turbine diameter of 0.5 meters, an impeller speed of 600 rpm, and a liquid viscosity of 0.1 Pascal second, and a liquid density of 1000 kg per meter cube. The effect of gravity is negligible. If the power required in the lab scale model is P1 and they estimate the power for the actual application is P2, then the ratio of P2 by P1 is option A 10 to the power 3, option B 10 to the power 4, option C 10 to the power 5, Option D, 10 to the power 6. The trick to solve the problem is to develop a formula for agitator power in terms of the data given. We will use the concept of dimensional similarity to develop the formula. The rotor power for an agitator is determined from the formula P equal to Np times rho times n to the power 3 times d to the power 5. Where P is the power in watts, Np is the power number, rho is the density of the fluid in kg per cubic meter, n is the rotor agitator speed, revolution per second, d is the diameter of the impeller or blade diameter in meter. The power number Np is obtained from charts provided for different types of agitator blades. We can rewrite the above formula for dimensionally similar geometry. P is proportional to rho times n to the power 3 into d to the power 5. P is proportional to Np. And also note that the power number decreases with increase in Reynolds number, Re. Np is proportional to 1 by Re. Re is equal to du rho by mu. U is equal to pi dn. Hence, Re becomes Re proportional to d squared n times rho by mu. Combining all the equations given above, we can write for power P, P proportional to rho times n to the power 3 times d to the power 5 divided by d squared n rho divided by mu, which simplifies to n squared d cube times mu. Now let us come to the data given in the problem for the two lab experiments performed with the agitator. Experiment 1. Agitator diameter d equal to 0.05 meter. Turbine impeller speed n is equal to 600 rpm. Liquid density rho equal to 1000 kg by cubic meter and viscosity mu equal to 0.001 Pascal second. Experiment 2. Agitator diameter d is equal to 0.5 meter. Turbine impeller speed n equal to 600 rpm. Liquid density rho 1000 kg per cubic meter and viscosity mu 0.1 Pascal second. Since the fluid properties and turbine or blade dimensions are different for otherwise geometrically similar agitator, that is, disk turbine in a baffled tank, the ratio of power P2 to the power P1 equal to N2 squared into D2 cube into mu2 divided by N1 squared into D1 cube into mu1. Substituting the data given for the two experiments in the above relationship, we get P2 by P1 equal to 600 by 60 squared into 0.5 cube into 0.1 divided by 600 by 60 squared into 0.05 cube into 0.001. The ratio of power Pt by P1 works out to 10 to the power 5. The answer to the problem is option C. GATE 2019, question number 41. A centrifugal pump is used to pump water of density 1000 kg per meter cube from an inlet pressure of 10 to the power 5 Pascal to an exit pressure of 2 into 10 to the power 5 Pascal. The exit is at an elevation of 10 meter above the pump. The average velocity of the fluid is 10 meter per second. The cross-section area of the pump at the inlet and the outlet is 10 to the power minus 3 meters squared, and the acceleration due to gravity, that is g, is equal to 10 meters squared per second. Neglecting losses in the system, estimate the power in watts delivered by the pump. The problem is schematically explained with a sketch as shown. The supply tank pressure P1 equal to 10 to the power 5 Pascal. Receiving or delivery tank pressure is at P2, which is equal to 2 times 10 to the power 5 Pascal. The receiving tank elevation is 10 meter from the discharge flange. The fluid velocity in the pipe is 10 meter per second. The cross-sectional area of the pipe is uniform throughout at 10 meters squared. Density of the fluid is 1000 kg per meter cube. Given that the value of d is equal to 10 meter per second squared, power delivered to the pump in kilowatt is determined from the formula bhp equal to 0.01 times q times ht times rho divided by efficiency. Where ht is the total head in meters, q is the volumetric flow in meter cube per second, rho is the density in kg per cubic meter, bhp is the brake horsepower in kilowatt. The volumetric flow rate is equal to area of the cross section of the suction or the discharge pipe times the velocity of the liquid, that is Q equal to U times A. Substituting the value of velocity and area cross section of the pipe, the volumetric flow rate is obtained. Q is equal to 10 times 10 to the power minus 3, which is equal to 0.01 meter cube per second. The total differential head Ht is obtained from the formula Ht equal to Ht minus Hs plus Hfs plus Hfd. The head terms are all in meters, but you must note that the heads are not directly given. You have to convert the suction and discharge pressures given to head terms using the value of the density and acceleration due to gravity. Likewise, convert the pressure units from Pascal to suitable metric units as shown. The HPS, the suction head, equal to 10 to the power 5 Pascal, which is equal to 10 to the power 5 divided by 1000 times 10, which is equal to 10 meters. The discharge head HPD equal to 2 times 10 to the power 5 Pascal, which is equal to 2 into 10 to the power 5 divided by 1000 times 10, which works out to 20 meters. The frictional losses HFS on the suction side, HFD, the friction loss on the discharge side, are 0. Neglecting the frictional losses, we have the suction and discharge heads Hs and Hd as Hs equal to 10 meter, Hd equal to Hpd plus the elevation from the discharge flange, which is Hd equal to 20 plus 10, which is 30 meters. So the total differential at Ht is equal to Hd minus Hs, which is 30 minus 10, which is equal to 20 meters. The power delivered by the pump is calculated from power equal to 0.01 times Q times Ht times rho. Substituting the values, you get power delivered equal to 2000 watts. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of career-oriented professional students. Thank you for watching.